Okay, we'll get back to section 2.2 here. We just finished problem 5, we made our histogram and relative frequency histogram. And remember that those will always be the same shape, okay? Now, problem 6, they want us to observe the distribution shapes for the variable that are mentioned on the next page, and then classify the shape of the distribution in question 5. Okay, so here's the next page. It says one way that a variable is described is through the shape of its distribution. A few of the most common shapes are shown below. It's important to recognize that the data will not always exhibit behavior that perfectly matches any of these shapes that are given. They're just, ways that we can identify the graph. But identifying the shape of a distribution is, there's some flexibility required, okay? And in addition, some people may disagree on the shape, since identifying shape is really a subjective thing. The first histogram is called our bell-shaped histogram. Now this one's going to be super, super important to us later on. Once we get into chapter 7, we're going to be doing things with the bell-shaped histogram for the rest of the course. So the bell-shaped histogram is if you outline the tips of the bars with a nice smooth curve, you get something that looks like a bell curve. Okay, so the bump in the graph is in the center, and now if all the bars are roughly the same height or exactly the same height, okay, we call that uniform. Okay. And if the bars kind of have a trickle upward effect, we call that J-shaped, and reverse J-shaped, okay, will be a trickle down effect, okay. Skewed to the right would be if the bump in the graph is more towards the left side than in the center, then you call it skewed to the left. Okay, skewed to the left means that the tail to the right of the peak is longer than the tail to the left of the peak. Okay, skewed to the left means that the tail to the left of the peak is longer than the tail to the right of the peak. Okay. There's some more. So bimodal, this is on the next page. Bimodal would mean that there's two modes, okay, and so there's two bumps in the graph. And U-shaped would be if the tips of the bars make the shape of a U. Okay. Now, honestly, in your book, your book chooses to focus on skew to the right, skew to the left, bell-shaped, and uniform. Okay. These other ones are kind of common ones, but your book doesn't talk about them at all. Okay, so if we take a look at problem 6, so we just looked at the distribution shapes. Okay, and if we observe the distribution shape for the histogram that we just drew here, what would be the best classification of this shape? Okay. Well, when I look, so, and by the way, it does not matter which graph I look at. Okay, so I can just look at this one. So this looks like it produces somewhat of a bell curve. Okay, I'm calling this somewhat bell-shaped. Okay, it's not perfect. It most of the time won't be. Okay, but it's somewhat bell-shaped. Okay, and I could also see an argument for calling this perhaps skewed to the right. Okay, the right tail does appear to be a little bit longer than the left tail. Okay, not by much, but you could call this perhaps skewed to the right. Okay, how big should class widths be? Okay, now in the book, your book will always tell you, use a width of 5 or use a width of 7 or 10 or whatever. Okay, but in general, like if you had a freedom of choice, how big should they be? Well, I've got it written here. So big enough to reveal interesting features about the data. There's no such thing as a correct width, but there can definitely be less desirable frequency distributions. In general, the width, the larger the width, the fewer the amount of classes. The smaller the width, the more classes there will be. Okay, so typically we prefer to have anywhere between 5 and 15 classes. Okay, so between 5 and 15 bars is typical of a histogram. Okay, now so what if I used a width of 20? Like here I'm using a width of 5. Remember, width of 5. And what if I were to use a width of 20? Okay, that would be a very, undesirable width, since I would only have a bar graph with 2 bars. Okay, and that wouldn't tell me a whole lot about what's going on here with the this distribution. On the other hand, what if I had what if I decided to use a width of 1? 1 is also not very desirable, since I would have too many bars. Okay, so our goal is to have between 5 and 15 classes, and again, there's no such thing as a correct width, but there are less desirable ones than others, though. Okay. So let's see, if we look at problem 7 next. It says, using a class width of 10, repeat question 5 for the frequency only. Okay, so question 5 was the information about Old Faithful, the geyser, and we just did that in the last video there. Okay, so we're going to use we're going to repeat that using a class width of 10. Which frequency seems to provide a better summary of the data? Okay, so in question 5, I made a frequency distribution and I drew the histogram. Okay, and so I'm going to do the same thing here, and then comment on the shape of the distribution. So the distribution is I again label the headings. Okay, so the seconds, I'm going 90 to 99 if I'm using a width of 10, because I want the next class to begin at 100. I'm going 100 to 109, 110 to 119, and then 120 to 129. Okay, using a width of 10. Remember how we define a class width. So the class width is the difference between consecutive lower class limits. Kind of quirky how we define it, but that's what we mean. So I'm using width of 10. And then I'm ready to give the frequencies. So I've got 7 numbers that are in the first class, 28 in the second class, 8 in the third, and 1 in the last class. And by the way, how am I getting these numbers so quickly? Well, it's because I've already made this distribution. So if I add 4 and 3, I get 7, right? And I said there's 7 in the 90 to 99 range. 17 and 11 gives me 28. So there's 28 numbers in the 100 to 109 range. There would be 8, 7, and 1 in the 110 to 119 class. Okay, and there's 1 in the 120 to 129 class. Okay. There's 44 eruption times listed, and that's what I had before. Okay, and so I'm ready to make my histogram. Making a bar graph, the bars touch each other. Remember that we always use the lower limits for the values on the horizontal axis. So I'm going to start this at 90, and by the way, that's because the lowest eruption time listed in the data set is 90. Okay, and I believe we've got 2 of them, right there and right there. Okay, and then 100, 110, 120. Now I don't have it listed, but if I were to include a 5th class, it would start at 130. Okay, and that's because I want to make sure to include everything in the 120 to 129 group. Okay, so that just says where the next bar would begin. Okay, and I've got my axes labeled. My number lines look good. The length of an eruption, which is in seconds, and the frequency, and I'm choosing an increment of 7 here on the scale, so 0, 7, 14, 21, 28. And by the way, we talked about this break in the graph. So that, again, is just a way to indicate to the reader that, hey, I'm not going to start this axis at 0, but I'm going to start at some other number. Okay, like this one, I'm starting at 90. So, I don't want this histogram to look silly. If I start at 0, that would look really silly. Because here's 0, the 90 is way out here. Okay, so I wouldn't have a histogram that that is way out here. Okay, that looks very silly. So that's all I mean by the break in the graph. It just tells the reader, hey, just take into account that we're not going to start the axis at 0 where we normally begin. We're going to start at some other number. And you could also include a break on the vertical axis too. So a histogram might have 2 breaks in it. Okay, and we'll see that on occasion. And okay, I'm ready to draw my bars, and the bars touch each other. The width is the same throughout. Okay, so I've got 7 numbers in the first class. I need a bar at a height of 7. 28 in the second class. I need a bar at a height of 28. 8 in the third. Okay, I've got and then 1 in the last. Okay, and now it says, which frequency distribution seems to provide a better summary of the data? Well, it looks like if we were to classify this distribution, I would say that this is bell-shaped. Okay, and it's not a perfect bell curve, but it's more bell-shaped than this one. Okay, and this is the one where we had 7 classes in it. This one we only had 4 classes in it. So this one appears like it's more bell-shaped. Now, which one is better? Well, you can see that if we break the width down into a width of 5, we get something that's not necessarily bell-shaped. Okay, we could call it perhaps skewed to the right. By the way, these are the only 2 arguments that I would see for this graph. Okay, so I would say that the first frequency distribution gives a better summary. Okay, we have more bars to look at, but it's not obnoxious, right? It's not like there's 30-something bars. Okay, so and that can change our distribution. Okay. Let's see here. For the next couple of problems, it says for each variable, state whether you would expect a histogram of the data to be bell-shaped, uniform, skewed to the left, or skewed to the right. Okay, problem 8. The birth weights in pounds of babies whose term was 40 weeks. Okay, I don't know if you know anyone who's had a baby or if you've had a baby or whatever, but usually when the wife is pregnant, usually she goes 40 weeks. Okay, and now is it every woman goes 40 weeks? No. Some are going to go less than that, some are going to go more than that, but 40 is like an average, right? And by the way, I would call this bell-shaped because bell-shaped would be the best classification, meaning that the amount of women who have a baby that is less than 40 weeks is not drastically more or less than the number of women who have a baby that's more than 40 weeks. Okay, it's roughly about the same, I'd say. So, we're going to have a bump in the graph that is towards the center, and the bump in the graph is going to be around 40 weeks. Problem 9, the number of cell phone subscriptions each year since 1990. Let's see here. I would call this skewed to the left. So, in fact, I don't know anyone that does not have a cell phone. Okay, and so skewed to the left, we've got this trickle upward effect going on. Okay, and think about in 1990 what that was. I didn't know anyone that carried a cell phone in 1990. Okay, So we've had nothing but an increase in that. Problem 10, your car's speed on cruise control over a 10-minute interval. Okay, cruise control means that the speed of the car is not changing. Okay, so that would be uniform. If I create a histogram, okay, it goes 0 to 10. The speed of the car is not changing. Okay. Heights of basketball players in the NBA. So I would call that bell-shaped. Okay, the average height of somebody who plays basketball in the NBA, I would guess, is about 6'2", 6'3", 6'4", 6'5", maybe. Okay, and that, by the way, that's where the majority of players are at. Okay, anywhere from like 6'3" to 6'5", 6'6". Okay. Now, not everyone is going to be 6'3" to 6'5", 6'6". Okay, if they play in the NBA, there you got some people that are shorter than that, and some people that are taller than that, right? And the taller players are usually in the center. Okay, it's just most of the league is going to be around 6'2" to 6'6". Okay, so if I make a histogram of that data, most of the data is going to be right there in the center. And I've got to like over here would be these people that are more than 6'6", and over here would be these people that are less than 6'2". Okay, but I would say that the amount of people that are that play in the NBA that are more than 6'6" are not drastically more or less than the number of people that are less than 6'2". Okay, they're roughly about the same, right? Hearing aids of patients would be skewed to the left. Okay, and if the horizontal axis represents the age, and the vertical axis represents the number of people who have a hearing aid. Okay, usually older people have hearing aids. Okay, so there's gonna be more people out here. Okay, the bars are gonna be higher. We get towards the right side. Now, not everyone that is old has a hearing aid, right? There's some younger people who have a hearing aid too. It's just when just observing life. More people who are older are going to are going to be at least a candidate for wearing a hearing aid. Okay. The outcomes from rolling a die 10,000 times. Okay, you guys got nothing better to do in your free time, so you're just going to sit at the desk and roll a die for 10,000 times for the next 3 days, and that would be uniform. Okay. So if I just take a standard 6-sided die, it's not like I would see a 2 any more than I would see a 5 or a 6 or something like that. I suppose it could, but it's not going to be drastic. Okay, it's not like likely. So I would likely see all 6 of the values the same amount. Okay, roughly the same amount. I mean it's not going to be perfect, but roughly the same amount. Problem 14, IQ scores of 7th graders. Okay, so I don't know if you've ever taken an IQ test, but usually anyone who's average would score 100 if they take an IQ test. Okay, now if everyone takes an IQ test and they're in 7th grade, are they going to score 100? No. So some people are going to score more than that, some people are going to score less than that, but the average would be a 100, okay? I would call that bell-shaped, since most of the people who would take an IQ test are going to score around a 100, okay? But you got the people out here who are going to score more than a 100, and you got the people down here who are going to score less than 100, okay? But since the majority of people who ever take an IQ test are going to score 100, I'd call that bell-shaped. Problem 15, annual household incomes in the United States. Okay, so I have it skewed to the right. Now I sometimes hear bell-shaped for that one. Bell-shaped is not going to be correct because so when with the average household income, for annually would be, I think it's like $35,000 or something like that. Okay, and so you got 35,000 is right here. Okay, and then anyone who makes less than 35,000 in a year is gonna be out here. Anyone that makes more than 35,000 is gonna be out here. Okay, now the reason why it is not bell-shaped is because if 35,000 was right here, that would be that'd be like saying that the number of people who make less than $35,000 in a year is the same as the millionaires, billionaires in the world. I don't think so, right? I don't know any millionaires or billionaires, okay? Not unless they're people that I read about in the news, okay? But personally, I don't, okay? And so, the fact is that there's so few people who have, millions and billions of dollars, and so I would tend to think that we'd have something that'd be skewed to the right, as opposed to bell-shaped. Okay. We'll go ahead and stop right there in the notes, and I'll pick up with a stem and leaf plot in the next video.